Hello and welcome back. You might have noticed that sequences are a lot like functions. You have an input, which is the term that you want to look at, n equals 1, n equals 2, n equals 3, and so on. You have the output, which is the value of that term. And you can actually plot them like we did in a couple of videos ago on a coordinate system, where n is along the x-axis and a sub n is along the y-axis. So here's a picture of a sub n equals 1 over n. Here we have 1 over 1, which is 1, 1 over 2, which is a half, 1 over 3, which is a third, and so on. Well, this is a lot like the 1 over x function that's continuous on the interval from 0 to infinity. So you have, on the one hand, the sequence, 1 over n. On the other hand, you've got the function, 1 over x, the continuous function, 1 over x. So if you kind of go back and forth between these two and think about putting them together, the 1 over x graph is basically just going through the dots made by the 1 over n sequence. So, or you can think the 1 over n sequence is just a function that's picking out particular points at the natural numbers, so at the x values that have natural numbers, 1, 2, 3, 4, and so on, the counting numbers, as they're sometimes called. It's just picking out those points of the 1 over x graph. So if you're trying to evaluate the limit of a sequence, it makes sense that if you can write that sequence as a continuous function, you can just think about it as the limit of a continuous function. And when you do that, you can bring in things like L'Hopital's rule, which work only for continuous functions. So let's come back to the notes and take a look. Here we have a theorem that is connecting sequences and functions. It says, suppose that we have a sequence a sub n and a function f of x such that the two are identical for all terms past some point, past some n naught. This is kind of like the capital N in some of the other definitions. So this a sub n equals f of n is saying that the values of these a sub n terms are exactly the same thing as the y values of the function at those n values. So at n equals 1, the first term is equal to f of 1. N equals 2, the second term is equal to f of 2, and so on. So it's kind of like saying that the dots of the sequence are all lying on this function right here. Then we can say that if the limit as x approaches infinity of f of x equals L, so if the limit of the function is L as the input approaches infinity, then the limit of a sub n as n approaches infinity is also going to be L. In other words, the limit of the sequence will be L. So if the function values go to L, then the sequence values have to go to L as well, because the sequence values are on the function. They're riding on the function, so they're going to have to get closer and closer to L as well. Example 8 will give an example of where we're going to use this. So it says, does the sequence ln n over n converge or diverge? If it converges, what does it converge to? Well, ln n over n is a sequence, so it only has as possible inputs 1, 2, 3, and 4. You can think of it as the domain of that sequence function is the natural numbers, or the counting numbers. So it's kind of like a function, but just with a restricted domain, in a sense. Well, we can unrestrict that domain to think about it as a continuous function. If we think about the function ln x over x, then the sequence and the function are basically the same, just one has a smaller domain than the other. Here, the a sub n's are going to match perfectly the function values for all n greater than or equal to 1. That's your little n naught right there is the 1. Well, now we can evaluate this limit using the continuous function. So take the limit as x approaches infinity of ln x over x. This is a throwback to Math 180 when you had to evaluate these kinds of limits, which we had to do when we were talking about polar tangent lines and things like that. So the type of this limit is infinity over infinity. So we can use L'Hopital. which says we can take the derivative of the top and the bottom separately. And when we evaluate this new limit, the limit as x approaches infinity of 1 over x is 0. So the limit as n approaches infinity of ln n over n also has to be 0 because it's stuck on the same curve. All the sequence values are on the function. So to fully answer the question, we're going to say that this sequence ln n over n converges to 0. Done. But not with a video. Now, having gone through that process, we're often just going to skip a lot of this, defining it as a function and using this theorem explicitly. We're just going to take it for granted and treat n as a continuous real variable rather than a natural number. So that we'll be able to differentiate directly with respect to n, rather than having to change the variable into x. Either way is fine. You can do it the way we did in example 8, or you can do it in this new way that we're going to talk about and show in example 9. But it's much easier just to think about n as a continuous variable and differentiate it directly rather than rewriting in terms of x. Just saves you some writing. So in example 9, we're looking at, does this sequence a sub n equal n plus 1 over n minus 1 all raised to the nth power converge or diverge? And here it's probably worth it to note what happens when you take the limit of the base, so of just the thing inside the parentheses. Well, that limit is going to be 1 inside the parentheses. The way you can get that is either by noting that the degrees on top and bottom are the same, so you can just divide the leading coefficients. 1 divided by 1 is 1. Or you can go through that whole trick that we were showing in a previous video, where you can divide top and bottom by n and then take the limit as n approaches infinity of the top and the bottom, and you'll also get 1 if you do it that way. Now the exponent is going to be going to infinity, because here all these limits that we're taking, we're letting n approach infinity. So this is a 1 to the infinity type limit. That's indeterminate. It's hard to know if that converges to anything or if it diverges, or if it does converge, what does it converge to? Hard to know. It's indeterminate. So there are a trick here in those kind of cases. If you think back to Math 180, is to use the logarithm to bring that exponent down. So we're going to use the log property to bring this exponent down. Now we're going to get a different kind of limit. So when we take the limit as n approaches infinity of ln a sub n, oops, the type of this new limit is going to be, well, the n's are going to infinity. And then if you look at the n plus 1 over n minus 1, that's going to approach 1. And ln of 1 is 0. So the ln factor is approaching 0. So this is another indeterminate form, infinity times 0. And what we did in those cases was, usually we bring some factor, either the n or this whole complicated ln thing, down to the bottom of the fraction by flipping it. So in this case, the n is a little easier to flip down to the bottom of the fraction, and its derivative will be less complicated than if we dealt with the ln. So we're going to write this as ln of n plus 1 over n minus 1 over 1 over n. And what this does is it changes the type of the limit into a 0 over 0 type limit. The ln is approaching 0, the 1 over n is approaching 0 as n approaches infinity. And this is good because now we can use L'Hopital. We can use L'Hopital to take our next step. Now taking L'Hopital on the next step, L'Hopital, I should really say using the L'Hopital's rule. So using L'Hopital's rule is going to involve taking the derivative of that top natural log. And I'm going to do that off to the side. Notice that I'm writing the derivative of something with respect to n. So here again, we're treating n as a continuous real variable. So we're going to take the derivative with respect to n of ln of n plus 1 over n minus 1. This is going to look a little bit complicated, but there's something that we can do before we start taking the derivative to make our lives easier. We can use a log property to break this big log into two little logs. Chop it up into some smaller logs. Right? The log, if you have a division inside of a log, that can turn into subtraction outside the logs. Now we can tackle each of these derivatives separately. This is going to be 1 over n plus 1 and 1 over n minus 1 when we take those derivatives. Now it'll help to have these two fractions together. So let's go ahead and bring these together into a single fraction. And it turns out that the n's on the top cancel. So you just get negative 2 over n squared minus 1 on the top. Whew. That was just the derivative of the top function. Thankfully, the bottom function is a little easier. Negative 1 over n squared to take the derivative there. Remember, you can write n as n to the negative 1, and then you'll get negative 1 over n squared. Okay, now before we move on, we don't want to do another L'Hopital. We want to try to simplify first. So let's simplify by noting that the negative signs cancel, for one thing, and the n squared will flip up to the top to give you 2n squared on the top. Now we can apply that same trick of dividing the top and the bottom by the highest power that we see in the bottom, the highest degree term. So that'll be n squared. And we get 2 over 1 minus 0, which is 2. Actually, another thing you could have done is, this is like an infinity over an infinity at this stage, the 2n squared over n squared minus 1. That's infinity over infinity. You could use L'Hopital a couple of, or maybe one more time, and then cancel off the n factors, and you'll eventually get 2 as well. So there are different approaches you can take at that stage. But we're not done, because all we found was the limit as n approaches infinity of ln of the terms of our sequence. We want to know, what is the limit as n approaches infinity of a sub n by itself? What is the limit of our sequence by itself? So the last part of this is going to be doing just that. And the way we're going to do that is rewrite a sub n as e to the ln of a sub n. Seems a little bit strange, but notice we haven't done anything wrong. We haven't done anything bad. Right? E to the ln of a sub n is going to just be a sub n, because the exponential and the log will cancel each other out. They'll undo each other, and you'll just get a sub n. So we haven't done anything wrong, and even though it makes it look more complicated, this is a good thing, because we know exactly where the ln of a sub n goes to. That goes to 2 up on the top there. So this top part right here, this top part approaches 2 based on all the work that we just did off to the left. So then the limit of the original function approaches e to the 2, approaches e squared. And now we're done. And we can take a little break. But not yet, because I just want to talk about one more thing, which is a couple of useful types of sequences to know. So there's 3 to the n over n factorial. That's not the only one. You could think of variants of this, like 2 to the n over n factorial, or 5 to the n over n factorial. these kinds of sequences converge to 0. And that's because when n gets large, the n factorial grows faster than an exponential, like 3 to the n, or 2 to the n, or 5 to the n, even 1,000 to the n. The proof looks something like this. If you expand out what 3 to the n looks like in our example, it just looks like 3 times 3 times 3 times 3, and you have n of these 3 factors. N factorial, on the other hand, looks like 1 times 2 times 3 times 4 times 5 all the way up to n. That's just by definition what n factorial means. Now, this is going to be less than the fraction where we take all of these 5, 6, 7, and so on up to n. So the numbers that are past 3. So you take the 5, you make basically all of those, the 4, 5, 6, and so on, into 4s, right? This is going to make the bottom smaller, which makes the overall fraction bigger. But then if you notice, these first three pairs right here, the three factors on the top and the 1 times 2 times 3 on the bottom, those 3 multiply to 9 halves. There's a factor of 3 that cancels, and you just get 3 times 3, which is 9 over 2. And then the rest of these are just 3/4. If you break them out into separate fractions, this is 3/4 times 3/4 times 3/4, and so on. We could write this as 3/4 to the n minus 3. Now that's going to approach 0 as n approaches infinity. This kind of a fraction, when you raise it to higher and higher powers, the bottom is going to grow faster than the top, and so you're going to get this whole thing is dragged down to 0. Every time you multiply by another 3/4, you're going to have 3/4 of the original value, which is going to get closer and closer to 0. So 3 to the n over n factorial is going to approach 0 as n approaches infinity. What about n to the n over n factorial? Which one of these is going to win? Is it the n to the n gets bigger faster, or the n factorial? It's going to be the n to the n. N to the n means n times n times n times n, and there are n of these n's multiplied together. Whereas n factorial is just 1 times 2 times 3 all the way up to n. You can see that the top numbers are going to be much bigger than the bottom numbers, because the bottom only has a single factor of n, and all the rest of its factors are smaller than n, whereas every single factor on the top is going to have a matching n factor. So the way you could write this up is to break them up into separate fractions. You have n over 1 times n over 2 times n over 3, and so on. And this is going to be greater than if you had taken all of these denominators and made them bigger, like the 2 if you replace it with an n, the 3 you replace it with an n, the 4 you replace it with an n, and so on. So if you can replace all those denominators, and the original thing is bigger, the new thing that you have is even smaller. And if that new thing, that new sequence of terms is even smaller, and it diverges still, notice that here all the n over n's are just turning into 1s. We have times this n right here gives you n. N goes to infinity as n goes to infinity. So even these smaller terms right here, all this together is like one term, one formula for a sequence. Even this smaller sequence is going to diverge. It's going to blow up to infinity. So this bigger sequence has got to be going up to infinity as well. So n to the n over n factorial blows up to infinity. Or in other words, you can think n to the n grows faster than n factorial. Thanks for watching this video, and see you in the next part.